In fluid dynamics, laminar flow is characterized by particles moving in well-defined paths so that there is no lateral mixing. That is, adjacent layers slide past one another. It seems as if the flowing water is frozen in time. It is easy to doubt if these videos are even real, but they really are. This is a video of the water fountain in Detroit Metro Airport. Isn't it fascinating to see water so well behaved and precisely controlled? Well, that's the beauty of laminar flow. The simplest way to achieve laminar flow is by turning on a regular water tap and reducing the flow rate until laminarity is achieved. Something interesting happens if the laminar water jet is obstructed. Put your finger midway between the laminar flow and adjust the flow rate and the position of your finger to find a wave-like formation above the obstruction. This is different. It seems to be unlike any other typical wave. First, the axis of the wave is vertical. Also, the wave is static. It is not even a stationary wave where the amplitude of antinodes change with time. Thirdly, the wavelength varies as we move the obstruction up and down. The formation of these waves is the result of the interference of capillary waves, which are generated as the jet is disturbed by the obstruction and travels along the water column. So, what are capillary waves? By definition, these are waves traveling along the phase boundary of a fluid, whose dynamics and phase velocity are determined by the effects of surface tension. Phase refers to water here. Phase boundary is the surface, and phase velocity is the velocity of wave propagation. We can generate capillary waves on a body of stagnant water by gently tapping its surface or putting a drop of water on it. We know the properties of a wave on string is determined by the tension in the string. Similarly, capillary waves are formed due to the surface tension of the fluid. Waves on the surface of water can also be due to gravity, which are called gravity waves. They have much larger amplitude and are formed when the disturbance is very large. For example, throwing a stone on the surface of water.
Back to the topic of this video. So when a jet of falling water strikes the surface of the obstruction, a capillary wave is generated which travels opposite to the flow of water. Capillary waves appears to be stationary, but these are the normal traveling waves. They appear to be stationary is because the fact that the velocity of the flow of the falling water is same as the velocity of the propagation of the capillary waves. We can briefly analyze the way the capillary waves are generated by the Young's Laplacian equation, which gives the excess pressure inside a closed surface. In the equation, gamma represents the surface tension. R1 and R2 are the orthogonal radii of the curvature of the closed surface. Suppose the lower part of the jet has a radius of r and it resembles a cylindrical water column moving down at constant velocity v. At the circumference where the jet strikes the obstruction, the pressure is decreased since now R1 becomes R but R2 is negative as the water surface is bulging inward. This implies, according to the Bernoulli's law, an increase in velocity. Because of the continuity equation, the diameter of this particular circumference gets smaller. Their molecules of the jet surfaces are pushed inwards, generating these capillary waves. Angular frequency omega of this capillary wave is given by this equation. Here, k represents the wave number which is equals to 2 pi over the wavelength and rho is the density of the water. The velocity of propagation of wave is equals to omega over k. As we know, the velocity of propagation is same as the velocity of the flow of water jet. We can represent the wavelength in terms of the velocity. Wavelength can also be written in the terms of the flow rate q and the radius of orifice r. As we know by Bernoulli's theorem, the velocity of the flow of water increases as we move down the jet. This explains why wavelength of the capillary waves keeps getting smaller as we move the obstructions down and vice versa. Another interesting and unexpected pattern appears when a drop of surfactant is put on the surface of the obstruction. Capillary waves are formed after a certain height and the lower part of the column is smooth and stable as if the flow is undisturbed. The height depends on the flow of velocity and it increases as the velocity decreases. Before giving a qualitative analysis of this phenomenon, we have to notice some basic properties of surfactant, for example, soap molecules. Soap molecules on water surface are oriented vertically with their polar groups in water and their non-polar tail in air. These soap molecules tend to spread over the water surfaces rather than mixing with the whole. Also, they decrease surface tension of water.
When soap molecules are present on the surface of obstruction and water jet strikes it, these soap molecules quickly spread along the vertical jet surface due to their strong affinity to water molecules. For the soap molecules to climb on the jet, their spreading velocity should be greater than velocity of water jet. The long hydrocarbon tails of the soap molecules standing in the air solidify the water surface that seems smooth and stable. One can consider the soap molecules climbing along the water column to form a cylindrical shell whose interior molecules are carried down in the mass of water jet. Therefore, a state of dynamic equilibrium is attained as the soap molecules surrounding the water cylinder are continuously replenished by those lying on the horizontal surface of obstruction. This explains the perfectly still cylinder below the ripples. We hope you learned something new and thanks for watching.